Hello and welcome to your final lecture, Lecture 12, Exam Review. Today we're going to talk about the format of your final exam and the topics that you'll see on your exam. We'll talk about Quiz 12 because it's a little bit different than the other quiz that you've been doing. We'll talk about how to study for your final exam, and then we'll do a mini practice exam together. All right, so first the format of the final exam. So your final exam is 3 hours long, so you have up to 3 hours to complete it. It contains 30 multiple choice questions, which are quicker questions that don't require multiple steps, so they're not so long. But then you're going to have 2 long answer problems, so similar to what you would have seen on your tests. And just like on your test, you'll have to take photos of your solutions and upload them in Canvas and submit those. Okay, so the topics on the exam are all the topics that we've done in the course. So starting from unit conversion, solving linear and quadratic equations, trigonometry, which it would include SOHCAHTOA and Pythagorean Theorem. There's vector addition, 1D kinematics, 2D kinematics, which is the same as projectile motion problems. There's momentum and energy. There's forces. There was forces 1 and forces 2. And then there's going to be levers and mechanical advantage at the end. Okay, so it's basically everything that we've done in the course you're expected to know, and it's equally distributed amongst all the topics. So there's not going to be one topic that it's heavier or lighter in. It's going to be pretty evenly distributed. All right, so you still have a final quiz to complete, Quiz 12. And in Quiz 12, you're going to find that it's much longer than the other quizzes that you're used to. So rather than having 3 questions, you'll have many more questions. And the purpose of this is that it's meant to help you study for your final exam. So it's quite long. It's testing you on a bunch of different types of questions, similar to your other quizzes, but because it's so long, you'll have unlimited attempts, and it will be due the day before your exam at 5 p.m. So once you know your exam day, we'll set the due date for your quiz to be the day before at 5 p.m. All right, Quiz 12 is still being graded as a regular quiz, so it's being graded the same value even though it's longer than the others. All right, so that takes us to how to study for your final exam. So the first thing that we recommend is that you're going to study by completing Quiz 12 because, as I mentioned, Quiz 12 covers a range of topics intended to help you study for your final. After you're finished Quiz 12, make sure you're continually repeating Quiz 12. You're doing it over and over until you're happy with your grade. So I recommend you keep doing it until you're getting a really high grade and you're happy with that and you know how to do all the problems. Then I recommend that you complete all your lecture problems by yourself. So check to ensure that you got the correct answer after you complete each question. So try doing the problems first without watching the videos, and then check afterwards, make sure that you got the correct answers. Once you're done that and you still want more practice, you can start going into the tests. So you can complete all the tests. So you can look at your test, but you can also look at the test solutions, which includes all the different versions of questions that you might not have gotten on your own tests. So again, I recommend you try them on your own. So kind of hide the solutions and then check the solutions and the final answer to make sure you're getting them correct. After that, if you still need more practice, then start going through the homework again. So if there's any concepts you're still having difficulty with, then go through the homework in that section and practice so that you can practice some more. And finally, make sure you're getting enough rest the night before your exam because you'll perform a lot better. Your mind will be sharper if you get that rest that you need the night before. All right, so we're now going to complete a practice exam together, starting with some multiple choice examples. You'll see on your final exam that you have 30 multiple choice questions. We're only going to do a few here. The first question is, what class lever is represented by a triceps extension? Is it class 1, 2, 3, or 4? Okay, so I'm just going to draw or paste in here an image showing what a tricep extension looks like. Okay, so now let's think about what class lever is this. So in order to figure out what the class is, you need to think about where the fulcrum is located, where the load is, and where the effort force is. Okay, so the fulcrum is located right at the joint, which is right here. So I'm going to just label that with a little triangle and an F for fulcrum. The load is what we're trying to, like the force that we're trying to move. So in this case, there's a force that we're pulling on here. It's like the tension rope and the tension force in this cable, but this is the load. Okay, and then we have the effort force, which is the force of the muscle in this case that is actually doing the lifting, or that's able to move that load. So that would be this force over here. It's the force that's exerted by the triceps themselves. So this would be the effort. Okay, so if we think of what class 1, 2, and 3 is, we can use that flex word. Now X doesn't mean anything. There's no such thing as a class 4 lever, so that one is totally out. Class 1 is where the fulcrum is in the middle, class 2 is where the load is in the middle, and class 3 is where the effort force is in the middle. In this case, the fulcrum is in the middle, so that would make this a class 1 lever. So the answer is A. So tricep extension is a class 1 lever. All right, question 2. Two forces are acting on a 3 kilogram object. We have a 10 Newton force pointing up. So let's draw what that looks like. 10 newtons pointing upwards, and we have 18 newtons pointing downwards. So that one's a little bit longer, and it's pointing downwards. We want to know what is the acceleration of the object. So before we begin, we need to find, okay. Question 2. Two forces are acting on a 3 kilogram object. We have a 10 Newton force pointing up and an 18 Newton force pointing down. So let's draw a picture of what this looks like. 10 Newton force pointing up, 18 Newton force pointing down. And we want to know what the acceleration is of the object. All right, so for this, we're going to use F net equals ma, which is Newton's second law. And the F net, we can decide which direction we want to be positive. It doesn't matter what we say. Let's say up is positive. So to find the F net, we have two forces here. One is pointing up, the other one is pointing down. If up is positive, then that means that the 10 Newton force is positive, and the 18 Newton force would be negative. And that's what our net force would be. Equals the mass, which is 3 kilograms, times the acceleration. And we're solving for the acceleration. So on the left side of the equal sign, we can do 10 minus 18, which is negative 8 newtons, equals 3 kilograms times the acceleration. If you find it confusing to have units in here, you don't need to include the units. As long as everything is in SI units, you don't need to worry about including them. I'm going to divide both sides by the acceleration. Sorry, I'm solving for acceleration, so I'm going to divide both sides by 3 kilograms. I'll move over here. And so now I'm left with negative 8 over 3. I'm just going to type that onto my calculator, and I get negative 2.667 newtons per kilogram is equal to the acceleration, because the 3 kilograms cancel out. Okay, so newtons per kilogram is the same as meters per second squared. So we have negative 2.667 meters per second squared. We said up is positive, so since this is negative, we're going to rewrite it without the negative sign. But since it was negative, that implies that the acceleration is pointing down. So the answer is 2.67. We've just rounded it here in the options to two decimal places. 2.67 meters per second squared down. So it's D. All right, question 3. Convert 18.5 kilometers per hour squared to meters per second squared. All right, so we're going to first get rid of kilometers, so we'll put kilometers in the denominator. Instead of kilometers, we want meters. Now we'll write the equivalency. 1 kilometer is 1,000 meters. Now we want to get rid of hours because the SI unit for time should be seconds and not hours. So we're going to put hours in the numerator, seconds in the denominator. 1 hour is 3,600 seconds. But at this point, the hours squared will not cancel with the hours, so we have to square the entire bracket. So we're going to type this onto our calculator. So I'm just typing 18.5 times 1,000 divided by 3,600 squared. And I get 0.00143. My units now, the kilometers have canceled, the hours squared has canceled out with this hour squared, and I'm left with meters per second squared. So that would be D. All right, question 4. How much momentum does a 2.5 kilogram ball have if it is moving at 3 meters per second? All right, so momentum is equal to mass times velocity. As long as everything is in SI units, we can just plug everything in. So our mass is 2.5 kilograms, and our velocity is 3 meters per second. When we multiply those, 2.5 times 3, we get 7.5 kilogram meters per second. All right, so then that would be C. That's a P. All right, question 5. If the hypotenuse of a triangle is 13 meters, so let's draw that out. So this is my right angle here. The hypotenuse is 13 meters, and one of the other sides is 5 meters. What is the length of the third side? So let's call this X. Okay, so we know two sides of a right angle triangle. We're looking for the third side, so we're going to use Pythagorean Theorem. A squared plus B squared equals C squared. So the most important thing to note there is that the C is the hypotenuse. So hypotenuse is the side opposite of the 90-degree angle, so that would be this side over here. So we'll label that as C. And the other two sides are A and B. It doesn't matter which one's which. So I'm just going to write down Pythagorean Theorem. A squared plus B squared equals C squared. And now I'll just sub in the values. So my A is 5. Squared. My B is X, that's what I'm looking for, and my C is 13. Okay, so now I'm just going to rearrange to solve for my X. So I have X squared equals 13 squared minus 5 squared. I'll move over here. X squared equals, I'm just going to type this on my calculator, 13 squared minus 5 squared, and I get 144. I'm going to square root both sides to get rid of that squared. And then I should put a little plus or minus here. So now I get X equals the square root of 144 is 12. Now there's that plus or minus, but we're talking about the length of a side of a triangle, so there's no such thing as a negative length. And the units here are meters because that's the units of the lengths of my other sides. So the answer is 12 meters, so that would be D. Okay, number 6. A boy slides down a 6-meter long hill. So I'll just draw that. It's a 6-meter long hill, which is inclined at 30 degrees. So this is 30 degrees here. If he begins at the top of the slide, so he's up here. So this is his initial position. So his V initial, he begins at the top of the slide with a speed of 1 meter per second. What is his speed going to be when he gets to the bottom of the hill? Okay, so first you need to think about what kind of question is this. There's actually more than one way to do this problem. You can use 1D kinematics if you want. The easier way, I think, is to use energy. So we're going to use energy, and we're going to say the total energy initially when he's at the top of the hill is equal to the total energy final when he's at the bottom of the hill. Now we have 3 types of energy that we learned in this class. So we have kinetic energy, gravitational potential energy, and elastic potential energy. Initial is equal to those 3 energies added up, final. Okay, so now let's take a look at all the values that we know. Before we can do anything with gravitational potential energy, we need to define our reference height. So let's say down here, the bottom of our image is where the height is 0. So then that means that the initial height of the object, of the boy, is this height over here. Well, how do we get that height? The hypotenuse is 6, and we know an angle that's 30. So we're looking for this height over here. This height is the opposite side of 30. So when you're looking for the opposite side, you use sine. So it would be 6 sine 30. Hypotenuse sine 30. And if I type that up, 6 sine 30, I get 3. So my initial height is 3 meters. Okay, so I have an initial height. My final height is when I'm at the bottom of the slide, and that's where the height is 0 meters. Okay, initially my velocity is 1 meter per second. At the bottom of the slide, the velocity is unknown. That's what we're looking for. And in this question, there is no mention of a spring at all, so there is no delta x. Delta x refers to how much a spring has been compressed or stretched, but there's no spring at all, so delta x would just be 0 then. Initial and final, because there's no spring in the question. Okay, so now let's use that information to cancel out anything that we know is 0 in our equation that we wrote out. So our initial delta x is 0, so that means that our initial elastic potential energy must be 0. And our final height is 0, which means our final gravitational potential energy is 0. So that's gone. And our final delta x is 0, which means our final elastic potential energy is also 0. So that term is gone. And that makes this a little bit easier to work with now. So I'm just going to put in the formulas for each of these terms. So EK initial is 1/2 mv initial squared, plus UG initial is mgh initial, equals EK final, which is 1/2 mv final squared. Okay, so I'm trying to solve for v final. So I'm going to get rid of the half and then get rid of the m. So to get rid of the half, I'm going to multiply the whole equation by 2. And so I end up with 2 times a half. So 2 times a half is just 1 mv squared, plus 2 times mgh initial, which is 2 mgh initial, equals 2 times a half again is still 1 mv final squared. Okay, notice that there's mass everywhere in the equation. So in every term has mass in it. So that means I can divide both the left side by mass and the right side by mass, and all the masses cancel out. So we can only do this when mass is in every single term. So now our equation is a little bit easier. We have v initial squared plus 2gh initial equals v final squared. Now we can solve for v final, which is plus or minus the square root of v initial squared plus 2gh initial. Okay, so really all I did in the step before was take the square root of both sides. And then I rearranged so that the v final is on the left side of the equal instead of the right. Okay, so let's start to sub in all the values we know. V initial is 1 squared plus 2, g is 9.8, and h initial is the initial height, which was 3. And now I'm just going to type this all onto my calculator. Square root of 1 squared plus 2 times 9.8 times 3, and I get 7.73. And my units would then be meters per second. All right, so the correct answer is D. All right, moving on. Now we're going to move on to some long answer examples, things that you might see similar to on your final exam. Now remember, on your final exam, there's only going to be 2 long answer examples. We're going to practice with 3 right now, just so you get a little bit more practice. All of the long answer questions that you see on your exam will tell you that when you're finished submitting your exam online, you also have to take a photo of your solutions and then upload those solutions to an assignment Dropbox or a Dropbox that you see in Canvas, similar to what you've been doing on all your tests. Okay, so let's complete question 7 together. We have a hose lying on the ground that shoots a stream of water upward at an angle of 40 degrees to the horizontal at a wall, which is 8 meters away. The speed of the water is 20 meters per second as it leaves the hose. How long does it take the water to hit the wall? So we need to think of what kind of question this is. The stream of water is on an angle, and it's going sort of like this. It's going to go up, but because gravity, it's going to come back down. So this is a projectile motion question. So we're going to go through all the steps for a projectile motion question again. So the first step, step 1, was to draw a picture. And that's what we're going to do right now. So our picture should always have a y-axis and an x-axis. And it should have all the important information. So the water is at an angle of 40 degrees above the horizontal. The wall is 8 meters away. So this is the wall right here. And it's 8 meters away from where the hose was. So this would be 8 meters. And the speed of the water is 20 meters per second as it leaves the hose. All right, so that takes us to step 2, and in step 2, we draw a table. And our table has x and y columns. And on the left side, we have all the variables from the kinematic equations. Initial position, final position, initial velocity, final velocity, acceleration, and change in time. And now we're going to fill out our table with all the information we know. So for initial position, we can label it on our drawing, on our picture here. That's our initial position. And what is that point then? It's right at the origin, so it would be 0, 0. And this is our final position over here, and that point then would be, our final position is up here because that water is hitting the wall. It's not actually landing on the ground. So our final position is 8, comma, whatever we label this value as over here. Okay, so we need to put in something for that value on our graph. We can pick any variable we want. The question is, part B is asking how high up will the water hit the wall. So that's what we're looking for in part B. So we can pick whatever we want. That's the height of the water when it hits the wall, so we'll just call it h. Okay, so that's an unknown value. So that point then would be 8, comma, h. And now we can put in our 2 points, our S initial, so this is our X and our Y, 0, 0. And our S final, this is our X and our Y, so 8, H. Our V initial we have to decompose into X and Y components. So that would be X, and this would be Y. Our Y component is opposite of 40 degrees, and our x component is adjacent to 40 degrees. So when we're finding our x component, since it's adjacent, we would use cos. So it would be the hypotenuse, 20 cos of the angle, 40 degrees. And when we're looking for y, since it's the opposite side, we'd use sine, 20 sine 40 degrees. Our V final is the speed as the water is hitting the wall, and we don't know what that value is, so we're just going to leave that blank because we don't know anything about it. our acceleration for projectile motion questions in the x direction is always 0, and in the y direction is always negative 9.8 meters per second squared. And that's because acceleration due to gravity points down. Our acceleration is 9.8 meters per second squared. And we're saying that to the right is positive, and that's because we made our arrow in our picture point to the right, and upwards is positive because the arrow is pointing upwards. So that's telling us that we're assuming to the right and up is positive. So since acceleration is pointing down, the y component has to be negative. Okay, so that was step 2. That takes us to step 3. We don't know time. In step 3, we're going to solve for time. So we're going to choose the column that has the most information and solve for time. All right, so if we look at the two columns, the x column and the y column, which one has the most information? Well, the y column has this unknown variable here, h, but the x column has the value for that missing variable. So x has more information in it, so we're going to use the x direction to solve for time. So when we think about what it is that we don't know and we don't want to know, we can look at the column and we can see v final is the one that we don't really care about and we don't know it. So we're looking for an equation that doesn't have v final in it. We're trying to solve for delta t over here. So we do want delta t in our equation. So we're going to use the first equation, which is s final equals s initial plus v initial delta t plus 1/2 a delta t squared. And we'll start to sub in all the values that we know. So s final is 8, s initial is 0, v initial is 20 cos 40 degrees, delta t, plus 1/2 a is 0, delta t squared. So since there's a 0 multiplied by this term, all of it goes to 0. And we're left with 8 is equal to 20 cos 40 degrees delta t. We're trying to solve for delta t, so we're just going to divide both sides by 20 cos 40 degrees. So that these two cancel, and we're left with delta t equals, and now I'm just going to type this on my calculator, 8 divided by 20 cos 40. And I have 0.5221629 seconds. Okay, so I can round this number for this question, but in the part B, I'm going to need to use this. So I want to make sure I know all the, like a lot of the digits here. Okay, so that was part A, all of that. So I'm just going to label that as part A. Moving on to part B. So actually, yeah, part A was to find the time. Now B is how high up will the water hit the well? So in part B, we're actually now on to step 4. And step 4 is solve for the unknown. So what's our unknown? It was this h over here. And that's what part B is asking us for. How high up will the water hit the well? So now we're moving on to the y direction. And we're going to choose a kinematic equation so we can solve for our unknown, which is h. And notice again, so we found what delta t was now. It was, I'm going to just put it in right here, 0.5221629. And that's the same value in both the x and the y direction because delta t is a scalar value. It doesn't have x and y components to it. Again, v final is something that we don't know and we don't care to know, and we're solving for h. So when we do this, we're going to use the same equation as before, the one that doesn't have v final in it, which was the first equation. S final equals S initial plus V initial delta t plus 1/2 a delta t squared. So our S final is h. That's what we're looking for. Our S initial is 0 plus our V initial, which is 20 sine 40 degrees. Delta T, which is 0.5221629 seconds, plus 1/2. A is negative 9.80. And then delta T again is 0.5221629 squared. So now I'm just typing all of this onto my calculator. So I have 0, I don't have to type in, 20 sine 40 degrees times 0.5221629 plus 1/2 times negative 9.80 times 0.5221629 squared. And I'm left with 5.38 meters. Okay, so that was part B. It asked how high up will the water hit the well. Now part C is asking what is the velocity of the water as it hits the well. So we're going to move that to this area here. Now we're looking for the velocity. When we look for the velocity, it means we need to find both the x component and the y component of the velocity. So we're going to start with the x direction, and then we're going to find the y direction. So in the x direction, we notice that the acceleration is 0. If the acceleration is 0, then that means the velocity doesn't change. So that means the final velocity is the same as the initial velocity. So the final velocity is equal to the initial velocity, which was 20 cos 40 degrees. I'm going to type that up on my calculator. 20 cos 40, and I get 15.3209 meters per second. Okay? You can also show that using a formula if you like. So what formula can we use here? There's actually quite a few, but we need to have one that includes V final. So I'm going to use this one. V final equals V initial plus A delta T. So my V initial is 20 cos 40 plus A, and my A is 0, and my delta T is 0.5221629. So notice 0 times anything goes away, and I'm still left with 20 cos 40, which is 15.3209 meters per second. Okay, so regardless of how you do it, the final velocity is the same as the initial velocity, which is 20 cos 40, which calculates to be 15.3209 meters per second. So now let's do the same thing, but in the y direction. So we're solving for V final in the y direction. Let's use the same equation we just used. V final equals V initial plus A delta T, but this time we're using the numbers that are in the y column. So V final is what I'm looking for. V initial is 20 sine 40 degrees plus A, and A is negative 9.8 delta T. And delta T was 0.5221629. So I'm just going to type that all on my calculator. 20 sine 40 degrees plus negative 9.8 times 0.5221629. And I get 7.7386 meters per second. All right, so now what do I do with these two values? I know my x component of my final velocity, and I know my y component. What do I do with them? I need to add them up as vectors. So the question's not asking for my components of my final velocity. It wants the final velocity, so it wants to know the magnitude. It wants the velocity, that means it wants the magnitude and the direction. So if the x component we found was 15.3209, which way is that going? X direction is positive, so it's going to the right. and the y direction is positive, meaning it's going up. So this is my v final x, which is 15.3209 meters per second, and my v final y, which is 7.7386 meters per second. What I'm looking for is the hypotenuse, which is this over here, and that would be my v final. Okay, so I'm solving for v final. So what I should do is label my three sides. I know two sides of a right angle triangle. I'm looking for the third side, the hypotenuse. So that's C. The other two sides are A and B. So I'm going to say A squared plus B squared equals C squared. Sub in the numbers that I know. So my A is 15.3209 squared plus my B, which is 7.7386 squared, equals my C, which I'll just call v final squared. Okay, so I'm just solving for v final. To get rid of that squared, I'm just going to plus or minus square root the other side. And now the square root and the squared will cancel out over here. And so I'm left with v final is equal to the square root, and I'm going to type this on my calculator, of 15.3209 squared plus 7.7386 squared. And that gives me 17.16 meters per second. Okay, but since the question asked for the final velocity, I need to remember that I also have to include the direction, which means I need to find the angle from where that velocity vector begins. So that would be this angle right here. So to find that angle, I'm going to use tan theta. Tan theta equals opposite over adjacent. My opposite side, my adjacent side. So I have tan theta equals opposite, which is 7.7386 over my adjacent side, which is 15.3209. I'm trying to solve for theta, so I need to bring the tan to the other side, and to do that, I take the tan inverse of 7.7386 over 15.3209. I'm just going to type this on my calculator. Tan inverse of 7.7386 divided by 15.3209, and I get 26.80 degrees. So my final answer is that my final velocity, as a vector now, I'm including both the magnitude, 17.16 meters per second, and the direction. Okay, so how am I going to give this direction? How would I give that direction? So it's actually going to be, this is the positive x-axis if I were to put in my y-axis here, and my x-axis over here. So that's my x-axis. The velocity vector is above the positive x-axis. So I would say 26.80 degrees above the positive x-axis. Okay? So that's the final answer. So you can see this is a longer problem, much longer, and you're not only going to be graded for your final answer that you give, but also for all the work that you show. Make sure your work is organized and it's very neat so that it can be graded appropriately, and make sure that you're going through all the steps in a logical order. Okay, so that was question 7, our first long answer problem. Let's move on to question 8. So this should say 8 here. Okay, so you're at the hospital and you're attached to an IV stand, which is 3 kilograms. You decide to go for a little walk through the halls of the hospital, and as you walk, the IV line pulls down on the stand at an angle of 8 degrees below the horizontal with a force of 12 newtons. The coefficient of friction between the stand and the floor is 0.1. So first you're asked to draw a free body diagram of the IV stand. Okay, so this is the IV stand, this little dot. Now what forces are acting on it? Okay, the first force we're going to say is the force of gravity, which always points straight down. Okay, what else is there? So the IV stand is on the surface of the ground, so there's going to be a normal force, and that normal force has to oppose, or it has to be perpendicular to the surface, so it's pointing straight up. Okay, it also says that the IV line, okay, so it's like a rope, similar to a rope or a string, it's pulling down on the stand at an angle of 8 degrees below the horizontal. So that would imply that there's a tension force here, which is at an angle of 8 degrees below the horizontal, pointing downwards. Okay, and then there's also friction. So you're pulling down on this IV stand, but which way is the whole thing moving? It's moving to the right. And so friction is going to oppose that motion and go to the left. Force of friction. Okay. So now let's think about the size of force normal, the normal force, to see if it's appropriate the way I wrote it. So we have two forces that have x components and two forces that have y components. This tension force can be decomposed into Tx and Ty, where the hypotenuse itself is T. So if we think about the y components, we know that this IV line, the stand, it's not moving in a vertical direction. When we walk, we're walking sort of in this direction. So we're pulling down on the line, but we're moving it horizontally. So that means all the y components of these forces need to cancel out. So what are our y components? We have Ty and Fg, and then we have F normal. Ty and Fg are pointing down, and F normal is pointing up. So F normal needs to be bigger than Fg. Fg and Ty together add up to Fn, F normal. So I'm just going to make F normal look a little bit bigger than Fg. So it's kind of like this, F normal. Okay. So that was part A, draw a free body diagram. Next, we want to calculate all the forces. So let's move on to part B. So when we calculate the forces, I like finding force of gravity first because Fg always just equals mg. So it's simple. M is the mass, which is 3 kilograms, and g is 9.80. And when I multiply those, 3 times 9.80, I get 29.4 newtons. All right. Next, I want to find F normal. I can't find F normal until I know what Tx and Ty are, though. So let's find those. So my T, they told me, was 12 newtons. So this is 12 newtons, my tension force. So let's find Tx and Ty. So Tx is adjacent to the 8 degrees. So then that means I'm going to use cos. So it's going to be hypotenuse cos 8 degrees. So it will be 12 cos 8 degrees. I'm going to type that up. 12 cos 8 degrees. And I get 11.8832. Okay, then I have my Ty. My Ty is opposite of the 8 degrees, so it's going to look similar, but it's going to be sine instead. 12 sine of 8 degrees. So I'm going to type that on my calculator. 12 sine of 8 degrees. And I get 1.6701. All right, so now I know my Tx and my Ty, I should be able to figure out my force normal. So I know that my force normal has to cancel out with my force of gravity and my Ty, because there should be no net force in the y direction since the IV stand is not accelerating or even moving in the y direction. So that means that F normal has to equal Fg plus Ty. All the forces that point up have to equal all the forces that point down. So the only force that points up is F normal, and then I have two forces that point down, Fg and Ty. So my F normal is equal to Fg, which is 29.4, plus Ty, which is 1.6701. And when I add those together, I get 31.0701 newtons. All right, so I only have one force left, which is the force of friction. And we know that the force of friction is always equal to the coefficient of friction times the normal force. And the coefficient of friction, it tells us, is 0.1 times the normal force. This is a 0 here. That's a 0. 0.701. And that gives us 3.10701 newtons. All right, so now we know all of our forces. Next, we can move on to part C, and part C is asking us to calculate the net force acting on the stand. So we know that in the y direction, the net force is 0 because we made it so that the normal cancels out with forced gravity and Ty. So we're going to find the net force in the x direction. So I'm going to say positive is to the right, F net is equal to, now what are all the forces that are acting in the x direction? We have Tx and we have Ff. Tx is positive, so that one's going to be written as positive, and Ff is negative because it's pointing to the left. So I can say F net is equal to Tx, which I already found was 11.8832 newtons, minus Ff, which I just found was 3.10701 newtons. So I'm just going to subtract the two. 11.8832 minus 3.10701, and I get 8.77619 newtons. Net force, I need to give a direction for that. It's positive, so that means it's going to the right. So that was C. Now let's move on to D. So in part D, it wants us to find what the acceleration is of the stand. So for acceleration, we use Newton's second law, which is F net equals ma, and we can divide both sides by mass, and we're left with A equals F net over the mass, because the masses cancel. So I have A equals my F net, which is 8.77619 newtons to the right, over my mass, which the question told me was 3 kilograms. So now I can just type this on my calculator, 8.77619 divided by 3, and I get 2.925 meters per second squared, and that's to the right. And that's D. So now we have one more question, E. How far can you travel in 15 seconds? Okay. So the question didn't explicitly say this, but we're going to assume that we started off at rest. We're pulling on the IV stand with the net force that we calculated, which means we're accelerating at 2.925 meters per second squared. So for part E, we're going to write down all the information that we know. We want to know how far can you travel, so that's delta S That's my question mark, in 15 seconds, which is delta t. And we're going to assume our initial velocity is 0 meters per second, because it doesn't tell us how fast we were going to begin with, but it says you decide to go for a little walk, so we're going to say we started off not moving yet. And the acceleration we just found out was 2.925 meters per second squared. It's to the right, so we're going to say that's positive, because positive's to the right. So now we're going to figure out which kinematic equation we're going to use. The one variable that we're not looking for and we don't have is v final. So we're going to use the equation that doesn't have v final in it, which is delta s is equal to v initial delta t plus 1/2 a delta t squared. So delta s is equal to v initial, which is 0, delta t, which is 15, plus 1/2 a, which is 2.925, delta t, which is 15, squared. Delta s is equal to, I'm just going to type this on my calculator, 0 times 15 is just 0. So I have 1/2 times 2.925 times 15 squared, and that gives me 329.06 meters. So that's how far you could travel in 15 seconds. All right, so that's question 8 that we just did. Now we can move on to our final question, question 9. So in question 9, it says, Kinza, let me just fix that. Question 9, Kinza, who has a mass of 40 kilograms, leaps onto a 20 kilogram bobsled. With the bobsled, she then slides down a 50-meter long frictionless ramp sloped at 20 degrees and into a spring with a spring constant of 2,000 newtons per meter. If she leaps onto the bobsled with a speed of 12 meters per second, how far will Kinza compress the spring? All right, so this is a pretty complex problem. We have Kinza jumping on a bobsled first, and then together Kinza and the bobsled slide down the hill, and then they compress a spring. So what type of question is this? It's actually a two-part question. Part 1 is Kinza jumping onto the bobsled, and that would be a collision. She jumps, which is kind of like colliding. She jumps onto the bobsled. And then in part 2, what happens, Kinza and the bobsled, which are at the top of the ramp, slide down the ramp and compress the spring, and that would be a transfer of energy problem. Okay, so we're going to start with part 1. In part 1, we have an initial and a final state. Initial meaning Kinza and the bobsled have not collided yet. Final meaning that they have collided. And when they do collide, they're stuck together because Kinza is on top of the bobsled. So that would make this an inelastic collision. So we're going to say the total momentum initially is equal to the total momentum final. So we have the momentum of Kinza, so I'm just going to use K instead of 1 and 2, initially, plus the momentum of the bobsled initially is equal to the momentum of Kinza on top of the bobsled final, because they're stuck together now. So now we have M Kinza, V Kinza initial, plus M bobsled, V bobsled initial equals the mass of Kinza and the bobsled, because they're stuck together, times V Kinza bobsled final. So we're solving for that V Kinza bobsled final. We're going to divide both sides by the mass of Kinza plus mass of bobsled so that they can cancel out. Okay. And so we're left with the velocity of Kinza and the bobsled together, final, is equal to mass of Kinza, velocity of Kinza initial, plus mass of the bobsled, velocity of the bobsled initial, over their two masses combined. This should say bobsled here. Okay, so let's plug in our values. Mass of Kinza, 40 kilograms. Velocity of Kinza, initially, if she leaps onto the bobsled with a speed of 12 meters per second, so that's her initial velocity, 12 meters per second, plus mass of the bobsled. The bobsled is 20 kilograms. And how fast was the bobsled moving initially? Before she jumps on it, before the collision, the bobsled's not moving, it's just sitting there. So that would be 0 meters per second. Divided by the mass of Kinza, which is 40 kilograms, times the plus the mass of the bobsled, which is 20 kilograms. So what do we get here? 20 times 0 here is 0. So we have velocity of Kinza in the bobsled final is equal to 40 times 12, which is 480 kilograms, over 40 plus 20, which is 60 kilograms. And there's this meter per second that's at the top still. The kilograms cancel, and we're left with the velocity of Kinza in the bobsled final is equal to 480 divided by 60, which is 8 meters per second. All right, so that was part 1 of the question. Now in part 2, Kinza and the bobsled are initially moving at 8 meters per second at the top of the ramp, and then they slide down the ramp and compress the spring. So let's move on to part 2. I'm going to actually do it just to the bottom over here so that you can see everything. Part 2. So this is an energy transfer. She slides down the ramp with the bobsled, and she compresses the spring. So initially, Kinza is now on the bobsled at the top, so that's initially, and at the end, Kinza and the bobsled have compressed the spring, so it's a little bit squished. Okay, so now what information do we know? It says that the ramp is 50 meters long. So that's this distance from here to here. Okay. So before we begin, let's decide what our reference position is going to be. Let's say the bottom of the ramp over here is where the height is 0. So the initial height is when she's up here. So that's my initial height. And that would be this distance right here, which would be the opposite side of 20 degrees. So it would be 50 sine 20 degrees. What about my initial velocity? Well, we already found out how fast Kinza and the bobsled are going when they're moving together. It's 8 meters per second. Okay. Now when they're at the bottom of the ramp and they've compressed the spring to the maximum amount, what is their final velocity? Well, if they've compressed the spring to the maximum amount, then that means that they've instantly come to a stop. So if they've come to a stop there, then that means their final velocity is 0. If they haven't come to a stop yet, then that means they're still moving and still compressing the spring. But when the spring is compressed to its maximum amount, then the velocity of Kinza and the bobsled would be 0 at that moment in time. What about their height? Well, we said the reference height is at the bottom of the ramp, and that's where they're going to be when they compress that spring. So then their final height is 0 meters. What about delta x? Initially, the delta x would be 0. And that's because initially when Kinza and the bobsled are at the top of the ramp, the spring has not been compressed at all. So then that means that the delta x is 0. When they're at the bottom of the ramp and they've compressed the spring to the maximum amount, the question is asking us to find how far will Kinza compress the spring. So the delta x is our unknown value, and that's what we're trying to solve for. Okay, so now we know all of the values, so let's start writing out our energy equation. Conservation of energy states that the total energy initial is equal to the total energy final. So let's write down all of our types of energy. Kinetic, gravitational potential, and elastic potential. All of those initially equal the same types of energy final all added up together. All right, so now let's cross off the ones that are 0. Delta x initial is 0, so then that means that UE initial would be 0. V final is 0, so that means EK final is 0. And H final is 0, so that means that UG final is 0. Okay? Now, if you need an explanation for why they're 0, let's just write out the formula. So EK equals 1/2 mv squared, UG equals mgh, and UE equals 1/2 k delta x squared. So if delta x is 0, then this whole thing becomes 0. If h is 0, then this whole thing becomes 0. And if v is 0, then this whole thing is 0. So that's how we know if v is 0, ek is 0. If h is 0, ug is 0. And if delta x is 0, then ue is 0. Okay, so now that we know what our formula is, now that it's more simple, I'm going to plug in the equation. So ek initial is 1/2 mv initial squared plus ug initial is mgh initial equals ue final, which is 1/2 k delta x squared. We're trying to solve for this delta x over here. So I'm just going to rearrange the formula right now. I'm going to start by timesing everything by 2 to get rid of the half that's here. So 1/2 times 2 is just 1, so I have mv initial squared, plus I'm multiplying the second term by 2, so I get 2 mgh initial. And on the other side, the half times by 2 just gives me 1, so I have k delta x squared. Notice that I don't have mass in all my terms, so I can't cancel them out. I'm solving for delta x, so I'm going to divide both sides by k. And then after that, I'm going to square root, so I get rid of that squared. So I have delta x squared is equal to mv initial squared plus 2 mg h initial over k. Now I'm going to plus or minus square root mv initial squared plus 2 mgh initial over k. So my delta x is equal to plus or minus my mass. Now what is the mass that we're talking about? It's Kinza on the bobsled, so it's the mass of both of them together, which is 40 plus 20 kilograms, so 60 kilograms. The v initial is their speed when they were at the top of the ramp, which was 8 meters per second, plus 2. Their mass again is 60. G is 9.80, and the h initial was 50 sine 20 degrees over k, which is the spring constant, which should have been given in the question. Let's take a look. The spring has a spring constant of 2,000 newtons per meter, so that's what goes in the denominator here, all in a square root sign. So delta x is equal to, I'm going to type this on my calculator, the square root of 60 times 8 squared plus 2 times 60 times 9.80 times 50 sine of 20 degrees all over 2,000. and I have plus or minus 3.46 meters. So the question asks how much was the spring compressed. The plus really means that it was stretched by 3.46 meters. The minus means it was compressed by 3.46 meters. You just need to use your logic to figure out which one it was in this situation. We know that they're compressing the spring because they're just colliding into it. So we can say that the spring was compressed by 3.46 meters. And that's the final answer. So again, another long question here. That was our final question that we're going to do. And you can see the difference between the short questions, which will be multiple choice on your exam, and you'll have 30 of them, and the long questions, which take considerably longer to complete. We want to give you marks for all of the solutions that you show, so you need to make sure that you take a photo of your solutions and upload them in Canvas so that they could be graded. Okay, so I hope that helps. Thanks so much for watching. I hope you enjoyed these lectures, and that was the final one. So best of luck on your final exam, and have a wonderful break when you're all done your exams. You deserve it. Thanks so much. Bye.